Welcome, students. This is going to be the beginning of unit number 2. We're going to talk about atoms and elements. Some of the topics we're going to be discussing here are the structure of atoms. We're going to talk about elements, isotopes, and ions. And then in the second section, we're going to talk about atomic masses and molar masses. There is a first part of the chapter that corresponds to this unit, that is a history of the development of the atomic theory from the 19th through the 20th century. But I'm going to let you study that on your own, not because I don't think it's important, but because at this point in time, I'd rather focus on what we know. And then we'll have time later in the semester to study a little history about some other types of theories, all right? So please don't think that I'm dissing history here. I'm just saying I'm going to let you study this on your own. So at the beginning of the 20th century, here's what scientists had arrived at. That all matter was composed of submicroscopic particles called atoms, and the atoms were composed of three types of subatomic particles. Protons that have a positive charge, neutrons that have no charge, and electrons that are negatively charged and much smaller in mass than both protons and neutrons. After the experiments of Rutherford, the model was that the atom consists of a very, very compact nucleus in which protons and neutrons are located, and then the electrons are dispersed in some kind of spherical region in space around that nucleus, with the electrons really being very far from each other, I guess relatively. The average atomic radius is about 100 picometers. The nucleus is about 5/1000 of a picometer. And I've heard this said before, that if the atom were the Rose Bowl, the nucleus would be like a marble on the 50-yard line. That gives you a sense of the dimensions of the nucleus size versus the overall size of the atom. Although remember, these are incredibly small things. In terms of subatomic particles, this chart gives us information about them. Notice that the masses in kilograms and the charges in units of coulombs are numbers that are not very wieldy. So we're going to end up using actually what we call the atomic mass units to describe the masses of these subatomic particles. And in terms of charge, we're just going to assign a value to each. We're going to say the protons are +1 and the electrons are -1 charge. And if we were to need to change into actual units of charge, we can always convert them using the actual conversion here of the charge in coulombs. For practical purposes, let's say that the proton and the neutrons are almost about the same mass, and they are about 1800 times the mass of an electron. Do we have any evidence that this type of model is correct? Well, in 1981, Binnig and Rohrer developed a type of microscope that could quote-unquote see atoms. This is very similar to the way a DVD or CD player works. Essentially, you have a probe, which is essentially a tip that generates a potential between the tip of the probe and the surface of the substance being scanned. This is called a scanning tunneling microscope. As the probe scans over the surface, it encounters, crevices and, different differences in the surface there. And every time that the probe encounters that, in order to maintain the constant current, it has to adjust the distance from the tip of the probe to the surface. Those electrical impulses are converted into signals that are used to generate an image. And you can see on the right how the tip scans across the surface, in a pattern. And the system, the machine essentially tracks that movement and the slight adjustments that the probe makes and uses it to convert an image of the surface of that metal. In this manner, the scientists were able to generate the image of a surface of a gold foil. And as viewed by scanning tunneling microscopy, you can see that all of the surface consists of a regular array of spherical, almost spherical objects, and these are actually the atoms. Now remember, these are not the atoms themselves. This is an image generated by scanning the surface of the foil of gold metal. But it essentially proved that the model was correct and that atoms are, in general, spherical in shape. Now, we said in the beginning of our class that pure substances that are made of a single kind of atom are called elements. That is how we can define them. However, we can go a little farther than that and say that an element is going to be identified by the number of protons in its nucleus. The number of protons, we call it the atomic number. We're going to use the symbol Z, uppercase Z for that. And the element's name is abbreviated. We don't want to have to write out the names of the elements because scientists, for the most part, we like to keep things a little simple. And so we've created a set of symbols to represent each element. These symbols are usually 1 or 2 letters. Some of the symbols may follow the English name. For example, N for nitrogen, or O for oxygen, or C for carbon. But some of them actually follow either the Greek or Latin name. For example, silver is represented by the symbol Ag for argentum, not Si, which is actually the symbol for silicon. On your periodic table, which I'll talk about in the second section of this presentation, you can see that the periodic table consists of a set of boxes, and in each box you're going to see the symbol of the element typically displayed prominently in the center of the box with the name underneath and the atomic number at the top. So those are the symbols of the elements, and of course some of them lend themselves to very curious memes that I found around the internet every now and then. So here's thorium, americium, and iron. Avengers unite. Yes, anyway. Okay, so all of the atoms of a given element have the same number of protons, but they do not necessarily have the same number of neutrons. Remember, the protons, the number of protons, the atomic number, is what identifies the element. But you can have atoms with the same number of protons, but a different number of neutrons, and they are called isotopes. To represent an isotope, we use the sum of the numbers of protons and neutrons, and we call that the mass number. And we're going to call it, the symbol capital A, or uppercase A. Remember, an isotope of an element will have the same atomic number, but it will have a different mass number. As a matter of fact, all the known elements exist in nature, or in whatever form they're isolated, in more than one isotope. In other words, we don't know of any naturally occurring elements that exist as a single type of isotope. There's usually 2 or more isotopes for every element. Now we can use some symbols to represent all of this information. Again, remember, we're saying that the number of protons in the nucleus is the atomic number, capital Z. And then we have the mass number, capital A, which is the number of protons plus the number of neutrons, or essentially the atomic number plus the number of neutrons. And the way we represent is by using the following symbol. Okay, take a look at that. And in this type of notation, this capital X here stands for the symbol of the element. So, if it's carbon, it'll be C. If it's chlorine, it'll be Cl. If it's nitrogen, it'll be capital N, and so forth. On the top left, we have the mass number, and it won't be A, it'll be a number. And on the bottom left, we have the atomic number. It won't be Z, it'll be an actual number. Let's consider the element hydrogen. Hydrogen is known to exist in 3 major isotopes, and we can represent them here with the blue spheres representing protons and the red spheres representing neutrons. Notice that the first one, which has only 1 proton and therefore 1 plus 0 neutrons, a mass number of 1, that is the most abundant of the isotopes of hydrogen. We also have the isotope that is commonly called deuterium, This one has a proton and a neutron, therefore 1 plus 1 equals mass number of 2. Remember, we have the mass number here on the top, right? And then the other common isotope is called tritium, and this one has a proton and 2 neutrons for a mass number of 3. And this one has an unstable nucleus. In other words, this is what we call a radioactive isotope. It decays, it decomposes further. Now, how would you say these things? If you see the symbol, and not all the isotopes of all the elements have common names like hydrogen has with deuterium and tritium. How do you say it? Well, for example, let's consider two isotopes of carbon here on the top. Now, if you were to say this or write it down, how would you pronounce it? Well, you can say, for example, the isotope on the top left here, we can call it carbon 13 and the other one carbon 14. Notice the form X-A, which is a different form of saying it. You have the element, name, or symbol hyphenated with the mass number. So you can say C13 or C14. And that's how you would pronounce it. That's how you would say it. Notice the next ones here. These are two isotopes of chlorine. Okay, we could write them as chlorine 35, chlorine 37, or simply Cl35 and Cl37. All right. Now, in a neutral atom, the number of electrons is equal to the number of protons. That is because you want to keep the atom at neutral charge. You want to have as many negative charges as you have positive charges. So if the atom is neutral, the number of electrons can be obtained also from the atomic number because it'll be the same as the number of protons. And don't forget, we can calculate the number of neutrons because if we know the mass number and we know the atomic number, the difference between those two should be the number of protons. So a little practice here. I'm going to give you a few seconds to try this. How many protons, neutrons, and electrons are in this isotope? Again, we could pronounce it uranium-235 or U-235. Okay, number of protons, we get it from, that's right, the atomic number, which is that symbol there on the bottom left. So it'll have 92 protons. Since this is a neutral atom, in other words, it doesn't have a charge, the number of electrons should be what? Same thing, same as the number of protons, right? Now, how do we get the number of neutrons? Well, we have a mass number of 235, which is protons plus neutrons, and we have 92 protons. So essentially, the difference between those two should be the number of neutrons. 235 minus 92 is 143. So we have 143 neutrons in this isotope's atom. Let's try another one here. How many protons, neutrons, and electrons would be in an atom of C11 or carbon 11? Very good. Number of protons comes from the atomic number on the bottom left there, so 6. There's no charge on this atom, so it should have the same number of electrons. Very good. And the number of neutrons, very good, 11 minus 6, that's 5 neutrons. Okay, so you should be able to do this. Of course, a lot of these things you already had in your introductory chemistry class, so it should be just reviewing. Now, I've been talking about neutral atoms, and you might wonder, well, why are we even bringing this up? Why are we even asking whether there is or not a charge? Well, the reason is that many atoms actually do not exist in neutral form. In a neutral atom, the number of electrons is equal to the number of protons. In other words, it's designated by its atomic number, Z. But during many chemical changes, atoms can lose or gain electrons and become charged particles called ions. Positively charged ions, for example, the ion of sodium that I'm showing there, are called cations. And negatively charged ions, such as the one I'm showing there for fluorine, are called anions. So let's see how the process happens. An ion, therefore, is an atom, or actually, as we're going to see in chapter 3, a group of atoms that has a net positive or negative charge. In other words, there is an imbalance between the protons and the electrons. However, ions of a given element are only different in the number of electrons. Only the number of electrons changes. So an ion with a positive charge is called a cation. It is not formed by gaining positive charges, in other words, by gaining protons, because that would change the identity of the element. A cation is formed when a neutral atom loses one or more electrons. In other words, it becomes positive by losing negative charges. Let's consider an atom of sodium, atomic number 11. So a neutral atom would have 11 protons and 11 electrons. In many compounds, the way sodium exists is in the form of an ion that has only 10 electrons and therefore a net +1 charge. And notice the way we represent it is the symbol of the element Na with a superscript with a plus. We don't call it +1 or 1 plus because typically the number 1 is usually waived. We don't write it usually. It's implicit in most notations in chemistry. Now there's another possibility, which is anions. These are ions with a negative charge. These are formed when the neutral atom gains one or more electrons. So consider the element chlorine, atomic number 17, which means it has 17 protons and 17 electrons. In one of its forms, the chlorine actually exists as an ion with a negative charge. That means that it has one more electron than the number of protons, or 18 electrons. Notice we represent it with the symbol of the element and then a superscript with the charge. And again, we don't write it -1 or 1 minus. Let's practice a little bit, and I apologize, but I don't think this next slide made it to your handout, so you may have to get a little piece of paper or make yourself an extra screen or slide in your PowerPoint handout. Let's practice doing symbols with ions. Remember, we use symbols to represent isotopes, but the ones we did before were all with neutral atoms. Let's try one here with charged atoms, in other words, with ions. Here is an ion of magnesium. And notice the notation as far as the isotope is concerned. There's the atomic number on the bottom left, and there's the mass number on the top left, and then the symbol of the element, Mg. And again, don't forget, whenever you write symbols of elements that have two letters, the first letter is uppercase and the second letter is lowercase. So make sure if you write it by hand that it is obvious. You know, sometimes we write things, for example, you might write the letter M in a way that looks the same whether it's capitalized or not. So make sure that the first letter is obviously uppercase and the second letter is obviously lowercase, okay? Notice the way we wrote the charge as a superscript on the right side. And notice we didn't write it as +2, but actually 2 plus. The idea here is to make sure we don't think that what we're writing is an exponent. It's actually just a symbol of the charge. Okay, so let's analyze this isotope. We are saying that this is magnesium, atomic number 12. Therefore, it should have 12 protons. How many neutrons? Remember, it's the difference between the mass number, which is 24, and the atomic number, which is 12. So that's 12 neutrons. How many electrons? Well, notice that this atom is +2 charge. In other words, it's deficient in charges. Therefore, it must be having 10 electrons only. And therefore, there's an excess of 2 protons or 2 positive charges. Don't forget, you don't make cations by adding protons. You make cations by losing electrons, okay? Let's try another one here. I'm going to let you do this one by yourselves. Here is an ion of sulfur. How many protons? How many neutrons? How many electrons are in this particular atom? Tick tock, tick tock, tick tock. Okay, you should have it by now, right? So we have 16 protons, right? 32 minus 16, that's 16 neutrons. And electrons, careful, or as we say in my neighborhood, watcha. This is an atom that has an excess of negative charges, has two negative charges, must mean that it has two extra electrons, and so it has 18 electrons. Okay, we're going to stop right here, and in our next section, we're going to be talking about the periodic table. Thank you so much. I'll see you soon.